Okay, whatever you say now, you can go to jail. I'm not. No, this is how we no. This is how we put the communication.
Yeah. That is. I will go to my students. I will go. Yeah. I completely.
I agree myself.
You agree? Okay.
Yeah.
Very good. Otherwise, you don't need to.
Yeah. No graduation. Who is important thing?
That's the most important. Me? No. You were right the truth. Why don't you start? You have to celebrate the actor. Waiting for me. You're for me. I'm not supposed to be here. I just got a coffee. I will do this.
Oh, you're getting
I just make sure that there's no food. I just make sure. Otherwise,
You could send a picture.
But with GANs and everything, you can't trust it.
Right. When I think you guys are there, then I'm sure.
Yeah.
It's the sound system is bad here, right?
Possibly.
Sound system, I think we tested it and I think people can.
Should be.
They removed the.
They removed the
speaker. I don't know why. But,
Yeah.
You have to stay there.
Yeah, next to this.
I think Raul will take a picture, right?
Yeah, possible.
No need for.
Yeah, I don't know. When I checked the other day, it was that link, and now it's another one. I have no idea.
Where, I mean, that link, then another one, where, who is changing this? I don't understand.
That Zoom, I have no idea why. My link has always been this, the first one I sent, and right now I look at the invite link and it's different. So I have no idea why they changed it, to be honest.
I mean, in general, we are not allowed to change. If it is a really public thing, right? You don't know who, but the whole point of public is you don't know who is coming. And they should be just able to.
Maybe I should tell Monica.
I mean, this is not as worrisome. I don't know that this one thing, but yeah, in general, it's not a minor thing to just change the.
I agree.
So you made the link by complete schedule, right? Maybe that's how.
I made a what?
In Zoom, you have to click on schedule meeting, and then that will. You can't just do it. That's great.
I will tell Monica. Oh, he's here too.
Alberto, it works, I think.
It
right?
works? Can you hear me?
Yeah, I can hear you very clearly.
Nice. Good.
So you see, I have to be online. Otherwise, nobody is online.
No, actually,
I don't know what I can.
Oh, you can control the camera.
Yeah, I can control the camera too. Yeah.
Make it closer to you. I mean, change the.
No, it
You can
cannot.
also change the angle.
No.
Then you should.
I cannot both be online and get free coffee. This is not allowed.
And I think you need to change the angle a little.
Yeah, like it cannot zoom anymore. I can change the angle, but it
No,
cannot zoom
those
anymore.
don't zoom. I only need to see the other direction, the other direction.
The other one? Let
The
me
other
see.
direction, yes, so you should change the angle. So you will be on at the end, then people also can see the screen, right?
Oh yeah, the problem with the screen. So right now I'm sharing the screen. The problem is if I move the camera to share the screen, it cannot see anything because of the light. So
Okay.
there is a blank, completely
Sure,
blank.
sure, sure.
That's why I'm just sharing the screen directly.
Okay, so you already zoom in, right? That's the maximum.
Yeah,
you
that's the
can-
maximum zoom I can do.
Okay, sure, sure. No, you can do more, you see?
Alberto alternatively going to his office.
You can do more.
Yeah.
Yeah, it's nice.
Okay. What is my? Right now I cannot see me. Oh yeah. Okay. Oh.
Don't ask questions.
Are you serious?
Yeah.
Oh,
But I don't know whether you want to do it or not, because now you've already sent out an email and.
I have sent, no, I haven't sent out. I just sent out the email to the committee.
I don't know, up to you.
No, that's fine. Okay. I guess we're.
Question, but still, we are not going to ask questions.
Is Sharik on?
I think not yet. No.
Someone doesn't go to Alberto.
You're not here. I don't understand.
So which part of Spain are the samosas?
More of the south.
I don't know. There could be questions like.
Samosas in the morning. Yes. Hey, there you go. These are fresh. These are good. What about the 100 years, you know? Are you from South? Are you
Certain regions.
it's spicy? What?
You can see clearly it's clustered around the samosa.
Yes, we are the foodies. Okay, so he's shining. Are you in touch with shining?
Oh, no, I'm gonna send him a
You
reminder.
have to make sure, yeah. You can't start something like that.
Oh, that's something.
Yeah, that's fresh. They made fresh.
Yes.
Yeah, normally in the Indian stores, it would have been like a day old or something, you know, this one is made fresh. Yeah, how come one will did not get the, come on, right, come, come. You know, this, what is this Spinal Tap or one of these movies? It's like you take up on like all these spy movies and these guys are watching the prism binoculars, and then in front of the prism are these cows grazing, and one cow just, and when you show the binoculars, you show these round things on the screen, and one cow just crosses over the round. Like that. Suddenly one can come here, get like a samosa and then go back.
Hey,
Hi, Charlie. Can you hear me?
yeah, there were also two other people on the other link. I did ask them to join here.
Yeah, I sent another email to Monica for them to know. Yeah, I agree. There was a change. Yeah.
So if anybody else has that other link, just tell them to.
What?
Take care.
Alberto, why did you change the link?
Yeah, I have no idea. I checked yesterday about the link and now it changed again. I have no idea why, to be honest. Oh, sorry. I have no idea.
Juan, you can come by, get some samosa and go back.
I try to accompany people online. So
I
it's
know,
like
but
the
I mean, I
salad.
understand. What I'm saying is you have both worlds. You can come for samosas too. Barshin just said the samosas are very good. They are actually fresh. Yeah, get some. It's okay. It's okay. Anyway, you're in the two worlds. So you can come.
Oh, well, I send my students to represent me. Order samosa. Yeah, salad. So you cannot have samosa.
Yeah, I know. Unfortunately, neither do I have students, nor am I being able to go there in person to have samosa. So
Yeah, so I think these samosas are really good. But anyway. I don't think
good to know. Good to know.
Proposal. Anyway, so we are ready. Are you ready?
Yeah, I think
Okay,
so. I'll
so
try.
so let's get started. So Alberto is it's being recorded, right?
Yeah, everything.
Yeah. So Alberto is going to be doing his PhD proposal, analyzing failure modes of inscrutable machine learning models. I would suggest, unless the committee has a different idea, to have the public presentation first, and then we can have the questions on both the presentation and the comprehensive questions afterwards. If that's okay, we'll do it that way. Okay.
Okay. Yeah. Thank you for coming. Well, yeah, my name is Alberto Olmo. I'm going to be presenting my PhD proposal presentation today. Yeah. This work has been done in conjunction with Professor Surak Mampari at the Judson Lab. And the name, as he mentioned, is analyzing failure modes of inscrutable machine learning models. Yeah. So first off, I would like to start by defining what I mean with failure modes. And with failure modes, I mean those outputs given by machine learning systems that seem reasonable enough, but they are unintentionally produce unsafe output by themselves. So these failure modes, what can lead is to more like unexpected behavior of the model itself, because we don't know how it will behave. They can also propagate biases, as we will show later, and that means that we can lose trust in the system, and they will, of course, be more resilient to be used in high-stake scenarios where the stakes are high. So examples of these are this one paper called Gender Shades, where they evaluate three different models out there that are facial recognizers, where they show that these they come from IBM and Microsoft and Google, and this facial analysis show that they are way more skewed towards males and whites, suggesting that they were trained possibly with more of that kind of data, and that there is a lot of disparity between the accuracies of the white males and the other end of the spectrum, which would be women of color, for example. So this is one of the examples. Another one, we can see that when we have classifications that are inexplicable. So when a classifier just does a misclassification, which is way off from the actual one, like say an image of a wolf being misclassified as a dog is not the same as being misclassified as an airplane, for example. So this will also be a kind of failure mode. So now I want to say that these failure modes happen mostly right now because we are in like machine learning is still very inscrutable, even though we are getting higher prediction accuracies every time. These metrics are really not looking forward to make they are not making the models more explicable. In any case, they are doing the opposite, and this can then make more like them not being inscrutable nor explicable, make the unexpected failure modes to arise more often. So here I compiled some example machine learning models that, as we can see, in terms of the one that we are going to be addressing mostly today, which is deep learning and neural networks, is one of the most with the less notional explicability by themselves, but with prediction, although their prediction accuracy is the highest, they are still very inexplicable and inscrutable. So then in this dissertation, we are going to show the failure modes that can happen from three main neural network implementations. Those are, in the first case, for large image classifiers, as I mentioned before, in the case of making misclassifications, when they make misclassifications more egregious than what they should. then in that sense, we also we will show that we design some methods to make them the classifications more explicable. Then we also talk about generative adversarial networks where they happen to have this failure mode called mode collapse that exacerbates the biases that exist in the training data originally. And we empirically show this by testing on 5 different GANs, including conditional and unconditional GANs. Finally, we also have we also evaluate the LLMs in specific GPT-3 and on both the structure and reasoning tasks. And we show that even though LLMs, or in this case GPT-3, can perform quite well on this action instruction task, they're still very, very sensible to prompt engineering. So we'll comment on that as well. So first off, I want to start by showing the work on analyzing the failure modes in those large image classifiers. And once again, I would like to just give the brief idea of what we were doing here, which is, so unless classifiers are 100% accurate, they will always misclassify, that's for sure. So it is, the idea is that it's better if for the human to not lose as much trust in the system, or even for it not to be unsafe in the future, like if we use it as like in driving cars, for example, it's better if these classifiers misclassify toward more explicable classes. Say, for example, in this case of this cat right here, we can see that the original model said, well, the ground truth is a tiger cat, while the original baseline model said it's a shower curtain. And after our trained data sets, to make them more explicable, it says it's a tabby, which is a kind of a cat. In this case, we could show that it's certainly more explicable that it's a shower curtain. So once again, these models are being trained mostly on just accuracy metrics and their effectiveness like that. So we want to make them such that they look at other metrics as well. So
is anybody controlling the Zoom? Somebody has to admit, somebody is get into this. Yeah, go ahead.
oh, okay.
That's okay. Go ahead.
Okay. So now what we want to do then is capture this explicability from the human model itself. Like, what would humans consider as explicable? Now, in terms of if we want to do this, we design a spectrum. We design 3 different kinds of tasks to get the human model that go from more task specific to more generic. In this case, the more task specific one and the more costly as well is at the instance level, where each human will evaluate each individual instance in the training or testing set, and will give their own reaction or the class that is that they think is in the image. This one is, of course, it doesn't scale well at all, but is the way of getting the mental model of the. Yes.
No, I can't admit it.
Oh, really?
Yeah, no, but you are.
You can also make me co-host.
Can you
I
make
can
me
do-
the host so that when people come in, I think they can get it.
Okay. Yeah. Thank you. Yeah.
Just make one of the people, maybe
Where participants?
Not here.
Oh, not here.
participants.
Oh, yeah.
Yeah, make
Yeah.
What is?
more.
So they don't want to see us?
No, somebody has to let people in while the talk is going on.
Oh, yeah, co-host. Yes.
Okay, good.
Thank you, Sean. Yeah. So as I was saying, this at this instance level, it's really costly for us to get this the mental model of the human. So we design a second less costly one, which is one level above of abstraction, which is at the class level. Now, instead of asking for every individual instance, we give the class names and ask the human to say how explicable this class is when it's misclassified to any other class, how explicable that is when it happens. So in this case, it is less expensive, of course, and it will scale better, but still, if the amount of classes is large enough, it's not going to be scalable. So finally, we designed a third one, which it's at the expert knowledge level, where we leverage, in this case, is WordNet for using their ontology. And in this case, we just measure the distance between each class pairwise to get this so the farther the two classes are, the more inexplicable we consider they are as well. So in this case, we avoid using human evaluations at all, and this can be scaled to any amount of classes, so long as they are in the WordNet ontology as well. However, it may, of course, not represent as well the human model. Then once we get these pairwise similarities, what we can create now is the mental model of the human in a confusion, in a pairwise ways, which is represented for us in a confusion matrix. Then, given that we now have the confusion matrix, we change the categorical cross entropy loss for it to account for this difference in weightings, depending on how egregious the misclassification is when it happens. And we show, well, that this egregious mistake should make the loss infinity, while the explicable ones should be less important than the inexplicable ones. I also want to mention here the two main, the objective metrics that we use to measure explicability, which are these what we call the soft and hard scores, where the hard score is basically each classifier will get, or the classifier in particular will get a score of added by 1 for this hard score, when it's the one that had, out of all of the classifiers, the one that had the most explicable misclassification. For the soft case, it's virtually the same, but now instead of adding 1, we divide by the amount of classifiers that at the same time were misclassified to the most explicable, which can happen. Several classifiers could be giving the most explicable misclassifications. So now that we know how we are going to train our models, which is adding these confusion matrices with the weighted loss functions into the models, I'm going to present what models we evaluated on. And these are, we used ResNet v2, VGE16, and Inception v2. And for this, for the first column, we only did on CIFAR 10, which was small enough data set such that we could use the IHL at the instance, class, and expert knowledge levels. However, for VGE16 and Inception v2, given that we use CIFAR 100, which has 100 classes, and Inception NIMETSNet, which has thousands, we could only leverage our expert knowledge level due to the costs of making at the instance and class level. We also wanted to make sure that the classifiers would misclassify as much as possible. So we used out of distribution data sets such that there will be more misclassifications than in the original ones. And that's the ones in blue, which are CIFAR 10 plus, CIFAR 100 plus, and NIMETSNet. Now, in order of the evaluations that we took, we evaluate in 3 main dimensions, which are the cost of labeling, in this case, the amount of labeling, human labeling intervention, the explicability measured with the dimension soft, hard, and scores, and human rated scores directly asked to them, and functionality given as per top 1 accuracy scores. We also do some RACAM evaluations, which I will comment on later. And yeah. So in terms of the human experiments, we have we ask around more than 50 plus mechanical torques. We want to directly measure how humans would themselves feel that or think that these classifiers are being more explicable than the baseline. So we give them the examples. We give them the misclassified, a set of 50 misclassified samples where they can give, where they will give their opinion on whether the baseline or without them knowing which one is which, they will give us their score on which one is more explicable. So for example, for this ImageNet, we give this misclassified cat, which was, this misclassified cat, which was misclassified by the baseline saying that it's a computer keyboard, while in our case, it was misclassified as a tiger cat, and then we asked the human. The same we do for CIFAR-10, although we add, now that we have available the 3 models, we also add the other remaining 2 that we trained. So now we also wanted to compare side by side how VGG 16, for example, and the vanilla VGG would compare in terms of accuracy and explicability. So yeah, we run the experiments and see that our VGG EKL with our trained loss function shows more explicable misclassifications, while vanilla VGG does it at a smaller rate than our own one. We also can note that the accuracies that we get for both are mostly the same, even happening that we get slightly better for our case, and then while preserving more explicable hard and soft scores than the original. Now, we also wanted to ask the question of whether or not we have our models were more looking at the right object when they are predicting, and we use GradCam, which is a saliency method that will tell us exactly where in the image the classifier will look at when predicting, and we compare our class level method with the baseline when both are incorrect, when one is correct and not the other, and when both are correct. And we can see in some cases where, like for example, in this column in particular, where this kind of bird, the baseline was looking more at the sky and some of the surroundings, while our method is looking more directly at the bird itself. This is just one example, but we can also see that this happens mostly for the ImageNet case. We can see it in this column here, for example, this one. And although further studies should be done to make like statistical claims about this. Then we come with the main problem of mostly at the instance level and the class level, which are the large amounts of human labeling intervention that we need. So we think that visual similarities could be leveraged as a way of extracting similarity between classes. So when humans feel that 2 instances are similarly visually similar, as I say, for example, in the case of a wolf and a dog, if they are visually similar, they would feel that they are not as inexplicable as they are when they are very far apart in terms of explicability, in terms of visual similarity, sorry. So we show that there are some works that already use visual similarities and encode them into this meaningful space, such that they can later get they can later use them as use the embedded space for their own purposes, and we can leverage this work as well for that. And I will show this in this slide where so the idea is to get this. What we want to do is to encode these visual similarities into the model. Into an embedding space, which will have the closer the instances they are, the more similar. So we can leverage that. We can use, for example, BGG, a dissected and trained BGG 16, for example. That's an available option. Or we could even train an autoencoder, which does the job of encoding the images into that embedded representation, even using our own loss function for that to happen there. Then once we have the encodings and the embedding space, we can later use things like similarity between the images to know at the pairwise level and compute the averages of the classes and at the instance level, what is their explicability. We can also use, for example, given that we have an embedding space now, we can also look at the neighbors for each class and then for each instance, and then see what would be what they are semantically closer to, and obtain another distribution from there. And this would, of course, reduce the human labeling intervention to zero, basically. Another idea is to use, now that we were using WordNet so far for the expert knowledge level, now, given that the rise of the LLMs, we can also leverage GPT-3 or LLMs as knowledge spaces. And we could certainly use them like asking them directly what is the distance to one another. But as we can see, for example, in the first two prompts, this can be noisy. So because here, for example, I asked first what is the similarity between dog and cat and dog, and they should be matching. But so there will be noising, and they are very prone to prompt sensitivity. So that's something we must have into account later. Now I'm going to be talking about the next set of work, which is about analyzing the failure modes, in this case for generative adversarial networks. And first of all, I want to again motivate the idea, which is that currently there is a lot of need for data, because neural networks or any other machine learning approach needs a lot of data to be fed and to have to predict, basically. So there has been the use of generative adversarial networks as a way of doing data augmentation. However, we believe that given that there are some failure modes that practitioners may not be aware of, they could be making their sample data sets worse or more skewed than they were before, as I will show later. Also, since they are very off the shelf available, these scans, anyone can use it. So we wanted to spread the word about this. So the idea is that many works have already pointed out this failure mode called mode collapse, where given that the discriminator and generator are not perfect, they will, as I will comment later, they make that skewed distributions would be not only perpetuated, the biases in the skewed distributions would not only be perpetuated, but even exacerbated. So yeah. So at first I want to more or less, sorry, to define what I mean with generative adversarial networks, just in case. And we have that these networks are two models, two neural networks working in tandem, where there is a discriminator just discerning between the training set, the image training set, or any data training set, and fake one. This fake is given by a generator, which is also connected and being feedback by the discriminator. And the idea is that the generator will be over time will get better and better at making fake images or fake data, and will be able to fool the discriminator at some point in time. The generator will just generate from random noise, or it can also be for the unconditional type of scans, or it can also be done with given some input data. I also put here their vanilla loss function, whereas we can see it's just a zero-sum game between the generator and discriminator. Now, the main issue is that when we give an unbalanced data set as the training set, we wanted to show that it will not only be, the biases will not only be put forward in this new data set, but they will be even exacerbated. So in this case, we just trained with a data set of professor faces from universities, I'll show later, for engineering professor faces. And as we can see already, the majority of people that are here are white male professors already, which is unfortunate, but yeah. And so this happens, as I mentioned before, due to this failure mode. This we discovered after making all of the evaluations and see that failure mode is the main, mode collapse is the main failure mode that causes this. And mode collapse, as an overall idea, it could happen in full or partially. In the case of the professor's data that I mentioned before, was happening partially, where we don't know over what dimensions exactly is collapsing to, but could also be in full, where all of the generated distribution looks the same. So the idea is that the problem with mode collapse is that, given that there are different sub-distributions, so as to say, on a training set, on any training set, the GAN will focus more on those that are larger than the minor ones, giving more feedback and more of the gradients to those big major modes, and forgetting more about the minor ones. And that's what happens when we input unbalanced data sets. So we evaluate on 5 different GANs. These first four are unconditional, or they come from the generator just generates from noise, while the cycle GAN generates from an input image. And these 3 in the middle also aim to tackle mode collapse, although, as I'll show later, they have their own caveats. So in terms of the evaluations, then, we gather from 47 US universities. We gather 17,000 engineering professor images, and only engineering professor images. Then we train the GANs that I mentioned before, get the sample distribution, and measure the final overall distribution. So we now wanted to evaluate how much biases were put forward by each GAN on both the gender and skin color features. And as we can see, the original one was 20% female facial features versus 80% male facial features. And both DC GAN and ADA GAN being one of the GANs that should be tackling mode collapse, both collapse further towards more masculine features. Program does so as well, but not as much. And then inclusive GAN match to do well. On the other side, for skin color as well, we can see that in this case, these 3 major DC GAN, ProGAN, and ADA GAN, the 3 of them collapse towards people of white color, which is the most predominant class, while leaving the non-white people to be the less one. We also want to mention that even though inclusive GAN does well here, we also show later that it has its own problems, like lack of diversity, or even it's very, very prone to poison attacks. So it's also not very suitable to use. Then we also want to experiment do further gender experiments with large, so that it's more automatic. We use the Microsoft Azure's Face API for that. And now because previously we did that, all of these experiments were done with MTARGs, just 50 images and 150 MTARGs. But now we wanted to know more about the gender skewness. So we use the MS API, and we show that for DC GAN, ADA GAN, and ProGAN, all of them are mode collapsing significantly. Finally, we also show that the cycle GAN, in this case, is a conditional GAN where you can give the input instead of this GAN being generating samples from random noise. And as we can see, there are many cases in which females are being converted to males with more male faces and features. And yeah, so we suggest, although we didn't do statistical studies on this, that it is still also mode collapse. So the consequences of that could be seen as, so Snapchat has its own filter, which we believe, although it's proprietary information, but we believe they may be using cycle GAN or some sort of conditional GAN. And as this filter, what does is to convert faces, picture faces, to their female counterparts. And once they do that, we could see that for getting when we look at this part of each image, we could see that they were making the color of the skin lighter, which suggests that they were also mode collapsing somehow towards lighter skin tones. We show this statistically with by making an experiment with 162 images, more than 30 per class, of non-white female, non-white male, and their counterparts, and we show that lighter that the filter lightens skin color, lightens the skin color towards non-white and non-white male and non-white female more than their white counterparts. So the key ideas from here is that even though we have GANs that palliate mode collapse, they have their own problems. Sometimes they don't palliate over all of the dimensions. And then the GANs that do suffer from mode collapse will inevitably bias further the possibly protect lab trees. Finally, I want to talk about how we analyze the large language models in this case. And we, for this, we initially set an experiment to know how well they would perform in the action extraction task, and which is basically extracting plans from natural language. Some of the issues or problem or difficulties that normally specific task extractors face, and GPT-3 as well, as we will show, is that the identification of the action names and parameters can be off, and the ordering of actions normally is not considered for that. So as an example, we would give, as an input example here, we will give the text, just plain text. In bold, they are marked the actions, and then but there should have been the actions there, but I don't know if I can show it. Okay. Okay, I tried. Oh, okay. So we can see so we can see now the actions here. But no, I don't like this.
I think you can reduce the participant figures to just one.
Really? Yeah. I think.
We need a couple more pandemics to get used to.
Yeah. Yeah. I'll leave it there for now. Yeah.
No, that's
Yeah.
not good. That's not
No, good? Okay.
Just get it in the bottom.
I have no idea how they
Go
are.
down, there's a down arrow right at the bottom.
No, but the down arrow doesn't do it, no. Oh, yeah. Okay. Okay, yeah. Sorry for that. Okay. Yeah, so so we leverage GPT-3 as the action extractor here. And overall, GPT-3 is designed to complete pieces of prompts that you can input without needing to tell any kind of instructions that I will show now. And it can be done in a few shot learning fashion. So for example, in this case, we would give the text, this text and actions as an example, and without saying anything else, we will give this next text and we'll leave this part blank, and GPT-3 will be able to complete it with what it understood from the previous example in this case, and we'll be able to get the actions and the according parameters basically. Yeah. So yeah, well, GPT-3 then it's has been trained on billions and billions of tokens from the common crawl data sets and Wikipedia as well. We are going to be using 4 kinds of flavors that it comes from. It comes with the most with more parameters is what is called the Da Vinci one, which has 175 billion parameters, and yeah. And in order to make the prompts to be as deterministic as possible, we use this set of this set of parameters so that we can replicate any prompts completions. Now we want to compare GPT-3 to the state-of-the-art task-specific extractors, and we do so by using the most used metrics, which in this case is F1. And we also take into account that there are 3 different kinds of actions, which could be essential, exclusive, or optional in this case. And we use also the most available and well used for comparison purposes data sets, which are these 3: Windows Help and Super Cooking Tutorial and WikiHow Home and Garden. So some of the results, they show that if we compare them to the task-specific extractors, which are the ones at the top, here we can see that GPT-3, the Da Vinci, these are ordered from more parameters to less. The Da Vinci one, which is the more powerful, so as to say, manages to get higher scores even on the Windows Help and Super domain, even more than some task-specific extractors. We see though that there is a certain significant drop for more complex data sets, because Windows Help and Super is a very simple data set, and even more so for action arguments. These are for the action names, and even more so for the action arguments where it's not as competitive for others. Then we also show how GPT-3, how the 4 main flavors of GPT-3 compare when given different types of different amounts of prompts, of few shot examples, and we show that it peaks at 2 or 3 shot examples. That's when it gives the most predictive accuracy. Finally, we also probe a little bit with using words like before or after to see if GPT-3 manages to understand order, which is something that normally task-specific extractors cannot do. And we show that for these examples, where we use the word before, it manages to reorder the actions. For this, we show that saying that it has to first do one action, then the other also understands it. And finally, this we use this another, like, anytime. You can do this action anytime, and you can see that it does the action at the very end. It decides to do the action at the end. So
I had a quick question. So for the first set of models that you have, which is like ES, DRL, what are these models exactly? Like, these are not language models, but task specific.
These are not language models. No. These are task specific ones. They have been trained. They have their own models themselves. Like, some of them are they are like neural networks and such, but they are only trained for task-specific purposes. Yeah, no, they are not like general, like GPT-3.
Okay.
Yeah. So then I want to show this quick example of how GPT-3 can also have failure modes when being used. And as we can see, I asked the question of whether or not is there any reason to believe that LLMs can support reasoning, and I add a final bracket at the end, and it gives a way different response than if we don't add this. This shows then that prompt engineering is something important in GPT-3, and then we should evaluate GPT-3 on other reasoning tasks, and then other unsafe and failure modes that we may not know about could happen still. So we should analyze better on, and we will propose now analysis on its reasoning capabilities. So as some examples of what we want to do for its reasoning capabilities, we want to see how well GPT-3 is at goal directed reasoning, for example, which is the most difficult or the most difficult task of them all, which is basically giving a state and then the goal, and asking GPT-3 to give us the plan. This is the most difficult and normally possibly the one where it will fail the most. But then we want to reduce the difficulty by, for example, giving an input plan with a completed plan and all, but then in the next case changing the order, for example, of the goal, and see if it can still understand that it's the same plan, or even making specific to general goals, like giving a specific, very specific goal, give the output plan, and see if again GPT-3 can generalize to a more general, which is still the same plan. Apart from those, we would also like to try other more tasks, like the completion of subset completion of plans. We will ask questions about we will reason about the optimality and different costs of the optimality of some plans, replanning as well, and then the execution reasonings about the resultant state of the executions of plan executions. So so finally, some of the conclusions we've seen that machine learning is still far from being inscrutable. It's still far from being explicable. So we definitely must make sure that we evaluate our output data always for any unexpected or unsafe failure modes, like the ones we have mentioned here. In this case, we mentioned these three failure modes that happen in large image classifiers that turn out to be more egregious, and failure modes that happen in GANs, in this case, the mode collapse. And we also analyze some data on structure and reasoning tasks for LLMs. In terms of the dissertation timeline, I would like to complete this proposed work by August of 2022, hopefully, then write the thesis by December of 2022, and hopefully present by December of 2022. In terms of my contributions and our contributions, to be honest, the first three are the ones that I've been commenting more in this work, but then I also had two more with my colleagues from the Georgia Lab. And yeah, so if you have any questions, I will be happy to try to answer. Thank you.
Okay, so we can now have like big questions, including of course the habit patterns. Also, I just realized that we forgot that we should clap up. You tried, okay, good. Go ahead.
So do you have the sense if training, when doing explicable misclassification, if it's significantly harder, because that loss function seems very similar to categorical processing. Do you have a sense of how much harder it is for a network? Like, what is the drop in accuracy?
There is some. Yeah, it's true. I didn't put the accuracy for all of them, but there is some drop. There is some drop on the accuracy, although it's compensated on the amount of explicability. But we had seen that at most it's like a 5% drop in for the CIFAR-10 classes, for CIFAR-10 data sets, for example. So there is a trade-off. Yeah, there is a trade-off. But we also show that for VGG, for example, the one that I mentioned here, it is the same. So I guess it also depends on the model itself. Yeah, that is true.
So just to follow up on that question, sorry, I'm not sure if somebody is talking from there.
No, please don't.
Yeah, just to follow up on that question, would you have any analysis or any other papers that have looked into like how the sample complexity of the problem changes based on if you change the loss function in this way? Because I'm thinking that if you do have more samples and you use this loss function, maybe there is a way to have similar accuracy, but just because the sample complexity of this new loss function or training with this new loss function is a bit more, and you don't have extra samples, maybe that's why you're seeing the drop in accuracy. Did you have any idea on like related work on those lines?
Related work on, can you say that again? On models that
Right.
show.
So if you use the weighted loss function, I'm just thinking that maybe that problem has a higher sample complexity than just training with categorical cross entropy loss.
I see, yeah.
And maybe that is why you see the drop in accuracy. And maybe one way to fix that, if this statement does hold true, is to have more samples. So let's say if you have 90% of the samples only for cross entropy loss and use all the 100% training examples for your loss function, maybe you'll have similar accuracies. So did you have any idea on that?
No, that's certainly a good suggestion, to be honest. Yeah. We did though, we at most what we did was to evaluate how much the loss function itself was being reduced, for example, in terms of we plotted the loss function itself, how much it was reduced at every point. But it is true that it would be a good idea to compare to other models that they do, that they do evaluate that. Yeah. Yeah.
Okay.
I have another one on. So your work has shown that different types of GANs, even if they try to avoid mode collapse, is a bad idea for data augmentation or building data sets. To use some of your phrasing, with the rise of foundational models, I don't like that word.
Did I say that?
No, you didn't say foundation.
Oh,
you
I
said
see.
LLMs. What about using more recently things like DALI and using text cues to say Cambodian women professor and generate data to try and combat biases that way?
Yeah, it gets
Do you have a sense of would that address the issues?
It could have their own issues as well, I guess. It may have its own issues,
Right.
which may not.
The skin lightening may still be there.
Yeah, things. It could. Yeah, any of that can happen as well, and we have to explore more. That like GPT-3 has its own issues as well, even though it can generate this new data. Yeah.
Thank you.
Yeah. Oh, yeah.
Big question. So you have one place to talk about coding visual similarity, right?
Yeah.
About that. So that's like an embedding space, also part of your training, or you use someone else embedding space?
So we would like to design two different ones. Both of them are related to the embedding space. One of them may come from a pre-computed or pre-trained model like BGG, which we can just dissect one of the layers in the middle and obtain the already pre-trained embedded space from there. And the other idea is to use an autoencoder to encode to get our own meaningful representation of the embedding space. Yeah.
Yeah, I guess the question is like it depends on the goal we train it.
Yeah.
Space.
Yeah, that's true.
Yeah. Sometimes the embedding space may not give you what you want.
Yeah, the idea is that, especially for the autoencoder, if we manage, we will have to make sure that similar clusters, visually similar clusters, are clustered together in order to get that.
One quick clarification.
Yeah.
Sorry, one clip.
Yeah. You can go ahead. Then
Oh. So should I go ahead?
Yeah, Shelly, you can go
Okay,
ahead.
yeah. Yeah. So one quick question was for the last work where you used GPT-3 to produce the action names and arguments. What was the number of samples you used for the few shot? Like, just curious there.
Yeah, it goes from 1 to 4. Here we show that no more than 4. After 4, it was not helping at all. So here you can see that, yeah, we were using from 1 to 4, and the peak is at 2 or 3 few shot examples per.
I see.
Yeah, for each one.
I mean, just wondering, like, till how much did you test? Like, because there has been some cases where it has been shown that, like, say for there is a peak at say 2, it drops down a little, but then it again increases after 10 or 15 maybe. And just wondering, like, because this is sort of an art with like both the prompt tuning and the number of samples on the few shot case. So just wondering, till how much did you try?
How much in terms of like prompts?
Number of samples. Yeah, number of samples where you give the prompt and the plan and just.
Yeah, it comes from here. Yeah, I think it was for, yeah. So we are limited by the amount of label text from each one. So in this case, we have these are the amount of inputs that we can get. Like in this case, like for Windows 7 Super, we have at most like 154 that we can try. It's at least it would be better if we had more, of course, but at least it could be significant to make.
Okay.
Yeah. Mansura, please. The expert knowledge one. Let me see if I can recall it.
Let's just go to the second part last. Second part.
I see. Second part and oh yeah, this one. Yeah. Is this one the one you mean? Yeah, it's why it's I was, to be honest, I was probing GPT-3 if it could give at least a reasonable output, like a score. Can it give like a score? I was trying to see that at that point, but it can be. We can of course change the question, and that's the idea of that. We have to change the. Why do you? Yeah, and it's always deterministic. In that sense, is deterministic. Yeah, we say. Yeah. We will have to do that certainly. If also because as you can see here, there is noise already. Like if I just move dog and cat.
It's not noise.
Well, it's.
Between the score of 1 to 10, how the dog is the same.
Yeah.
No, I think you should prime GPT-3.
Yeah, no, definitely we have to make prompt engineering. Yeah, a lot of prompt engineering.
Yeah, you could also prime it, saying that people are saying cats and dogs are similar. What do you think?
Yeah, also. Yeah.
It's kind of sad that we kept that level of prompt engineering.
Yeah.
Other questions? Okay. If not, then the public session is concluded. And then so what we will have to do is there is going to be a session for just the committee members. So you will turn this around so that all of us can be seen. I mean, those two people can't see us, right?
Oh yeah, they can.
While he couldn't see anybody. That's why Shailik is asking questions about other people.
I see. So you want? Oh, okay.
No, just turn the camera around.
Yeah.
And then also you should leave a laptop. That might be a okay idea too. I don't know. Yeah, that's Thank you.
Yes.
Yeah, you can leave it already. And then.
Yeah, you can be seen here.
Yeah, now I can be seen too, okay.
Yeah, let me see.
You can put on the camera.
I think I.
Oh, it's like a graph.
Yeah.
So I-
You can just do it.
Oh, so yeah. Oh,
Yeah,
okay.
yeah. So I think I don't need to unmute, right? Because the mic is here for everyone, right?
Yeah,
Yeah,
that's fine.
Yeah, that's good.
Now I cannot see Shailik.
Okay, now.
Yeah.
Almost everybody, who is Carl McPhee, who needs to get out?
Yeah, I'm gonna.
Host can remove it, right? Host.
Yeah, you should be removing everybody else.
I have a question to clarify. So for the last piece of work, you talk about the planning.
Yeah.
So what, can you show me a plan? Like what
Yeah,
is
an
the
example.
plan you extract from the GPT-3?
An example.
Just
Yeah.
1 second, it is a recording stop, right?
No. Oh, okay. Sorry.
You have to
Yes.
Stop the recording. This should not be-
Yeah. Sorry.
It's supposed to be recorded, it's not showing recording.
Yeah, it
no,
doesn't
should be
say.
saying, yeah, stop